Hello and welcome. In this video, we're going to review what an inverse is, what it means for the inverse of a function to also be a function, and how to check whether or not that's true, what inverses mean graphically, and then we're going to add in how you can use the derivative to determine if the inverse of a function is also a function. In the next video, we're going to start looking at how do we take the derivative, or how do we find the derivative of an inverse without actually having to find the inverse function. So let's go ahead and jump in. So let's review a little bit of concepts from previous courses. We learned all the way back in Algebra 2 that two functions are inverses if when you compose them or plug one into the other and simplify, you get x. This means that the reverse of that is also true. This is a biconditional statement. So two functions are inverses if and only if when you plug one into the other and simplify, you get x. This means that for every point that is a, b in f of x, there's going to be a point b, a in g of x. So really what we're saying is that we're switching our x and our y. Something important to note is that anytime you switch x and y, you have created an inverse. It's just not always true that that inverse is a function. The job of an inverse is to undo or reverse the operations of another function. Notation-wise, and don't let this get confused with the derivative, this f, it looks like f to the power of -1 or f superscript -1 of x. That is the notation for the inverse. In general, if the inverse function exists, then for any point x, y, there is also a point y, x in the inverse function. So how do we determine if two functions are inverses? What you do is you simply plug one function into the other. And simplify to see if you get x. If you get x, then they are inverses. If you do not get x, then they are not inverses. So let's go ahead and look at this example. Our f of x, which is 3x, and g of x, which is 1/3 of x, are they inverses? So what we need to check is what happens when we look at f of g of x, and we're also going to check what happens when we look at g of f of x. Actually, I kind of want that to be in a different color, g of f of x. Okay, so if f of x is 3x, then f of g of x, meaning I'm plugging this in for x in my other function, this is going to be 3 times the thing that I'm plugging in, which is 1/3 of x. Well, 3 times 1/3 of x is equal to x, which is what we needed it to be. So we have successfully checked that. If we're checking g of f of x, actually, let's just come down here. G of f of x means 1/3 times whatever I'm plugging into g, which in this case is 3x. And if I multiply this, this becomes 3x over 3, which is x. So these are inverses of each other, because when you take the composition of functions, it simplifies down to be x. So I'm going to encourage you here to pause the video and work through exactly what we just did. Plug f of x into g of x and simplify. Plug g of x into f of x and simplify, and see if both of those two things simplify down to be x. If so, the functions are inverses. If not, they aren't. So go ahead and pause the video. So here on number 1, if we plug g of x into f of x, we end up with the cube root of 2x cubed. Well, that's just going to end up being 2x. Divided by 2 is just going to end up being x. If we plug f of x into g, we're going to be plugging in x cubed over 2 into the x spot. The 2's are going to divide out, so I'm taking the cube root of x to the 3rd, which is x. If you haven't tried one on your own, I really encourage you to pause the video and do so now. So on number 2, if you plug g of x into f of x, you end up with 4x plus 9 minus 9 over 4. So the plus and minus 9 are going to add to be 0. and the 4's are going to divide out, so that works. If you plug f of x into g of x, you get 4 times x minus 9 over 4, so the 4's are going to divide out, plus 9. So we end up with x minus 9 plus 9, and that is also going to simplify to just be x. So now that we've reviewed a little bit about how to determine if two functions are inverses and the basic way that functions and their inverses behave, let's go ahead and think a little bit graphically about this and add in some vocabulary. So there's a fancy word for a function whose inverse is also a function, and that fancy word is invertibility. It sounds like a superpower, but it just means that a function whose inverse is also a function is said to be invertible. Something that you might be asking yourself is, how do I know if a function's inverse is a function, or how do I know if a graph is a function? And that's where some tools that we've learned in previous classes come in handy. An invertible function must pass two tests. It first must pass the vertical line test to be a function. So the vertical line test says, if I have, and I'm just going to use a quadratic function, if I have a graph and any vertical line I draw only hits the graph once, then this graph, which I'm going to call f, is a function. So it's a function if it passes the vertical line test. Any vertical line drawn on the graph of the function will only touch the function itself once. Then there's something called the horizontal line test, and the horizontal line test, you may have guessed it, behaves very similarly, except it says if we draw a horizontal line anywhere along the function and it touches the graph only once, then the inverse is also a function. So here, our function was f of x equals x squared. What we just learned is that the inverse of this is not a function because it doesn't pass the horizontal line test. So the f of x passes the vertical line test, but f of x does not pass the horizontal line test, which means that its inverse is not a function, which means that this function is not invertible because it doesn't go both ways. The vertical line test and the horizontal line test both have to work in order for a function to be invertible. So what kind of functions are invertible? You may realize that that means that if the problem here is that we change from going down to going up, any change in behavior will cause a function to not pass the horizontal line test. If I have a function that's just always increasing, then it's going to pass the horizontal line test. If I have a function that's always decreasing, this is not drawn very well, but that's going to pass the horizontal line test. So if a function never changes behavior, meaning it's either always increasing or always decreasing, it's said to be monotonic. So another new vocabulary word, monotonic, for the prefix mono, meaning one. It only has one behavior. It's either always positive, always negative, or always constant. And we can look at the derivative to tell us about the behavior, right? Because the derivative tells us where a function is increasing or where a function is decreasing. So we can analyze the behavior of the derivative to decide whether or not a function is monotonic. And if it's monotonic, then we can say that it's invertible. I know that's a lot of vocabulary, but we can say if something is monotonic, then it is invertible. So let's just briefly talk about how to think about inverses graphically, and then we will move to some examples where we look at whether or not a function is invertible or whether or not it's monotonic. So let's clear some space down here. Inverse functions are symmetric over the line y equals x, which is the line that perfectly stretches. I'm not going to try and draw it without a ruler here, but perfectly stretches along the middle here over the origin. So inverse functions are symmetric over the line y equals x. Since we just talked about how the job of an inverse is to switch x and y or to undo a function, we could easily find points to graph if we take points that are x, y, and we just switch the x and y to come up with new coordinates in our inverse function. So f of x is graphed down here. The first question we're asked is it a function? Well, it does pass the vertical line test here, so this is a function. Question B says, is the inverse a function? Well, does it pass the horizontal line test? It passes it here, but it doesn't pass it here. So the inverse is not a function. And then we're being asked for the domain of f of x. Well, it looks like the furthest to the right it ever goes is -1, and the furthest to the left it ever goes is -1, and the furthest to the right it ever goes is 3. And then we're being asked about the domain of the inverse, which we don't know yet. And I also sort of skipped over, given the graph the inverse. So let's go ahead and go back and do that. The very first thing that I'm going to do is I'm going to identify some points that are in f of x so that we can rewrite them as coordinates in g of x. So it looks like there are 1, 2, 3, 4, 5 key points here in f of x. So the first one I see is -1, -2. Then I see 0, -1. I'm just pulling these points off of the graph here. Then I see 1, -1. Then I see 2, 0. And lastly, I see 3, 1. So I'm going to translate these into coordinates in g. And to do that, I'm just going to switch my x and my y value. -2, -1. So -2, -1 is going to be here. This point is going to go to -1, 0 when I switch my x and my y. This is going to go to -1, +1. This is going to go to 0, 2. And this is going to go to 1, 3. And then I'm going to connect. Ooh, that did not go well. Let's try that again. I'm going to connect the dots there. And it does look like if I folded it along this line that everything would line up perfectly. So graphing the inverse really just means identify some points and switch the x and the y values. The only question we didn't answer about this was, what is the domain? What is the domain of the inverse? Well, the furthest to the left it ever goes is -2. The furthest to the right it ever goes is +1. So our domain would be from -2 to 1. And remember, you can also write this using interval notation if you prefer. Okay, let's get to the very last thing that we said we were going to do, which is determining if a function is invertible or determining if a function is monotonic given an equation. It's usually easy to tell what's going on from a graph because I can test using the vertical and horizontal line tests. But if I'm given a function, I don't really want to graph it. So there needs to be a way for me to discover that without having to graph it. Okay, so the directions here say determine, using the derivative, if the following functions are monotonic and therefore have an inverse. And actually, I'm going to add the word function. Everything has an inverse, but have an inverse function over their entire given domain. Find the inverse, whether or not the inverse is a function. Okay, so let's do this derivative part first, using the derivative. If I take the derivative here, I get 2x. The question that you're asking yourself is, does the derivative ever change sign? If the derivative is always positive or always negative, then that means that the original function is monotonic because it's never changing behavior. So ask yourself, if I plug in a negative number, what type of number do I get? If I plug in a positive number, what type of number do I get? Could I ever plug something in to make the derivative be negative? Could I ever plug something in to make the derivative be positive? And the answer here is that this is not monotonic, because the derivative could be positive or negative, depending on what type of number is plugged in. If it's not monotonic, that means that f of x, that its inverse is not a function. It still has an inverse. The inverse is just not a function, which also means that f of x is not invertible. But like we said, we can still find the inverse. So I'm going to let y equal x squared. To find the inverse, we simply switch x and y. switch x and y. And now we're going to isolate y. So I'm going to take the square root of both sides. So y is going to equal plus or minus the square root of x. That would be my inverse. Let's look at one last example. If we find the derivative here, the derivative is going to be 3x squared. Now I want you to think about what happens if you plug in a negative number, what happens if you plug in a positive number. Since what we're doing to the numbers that we're plugging in is squaring them, this is always going to be positive. The derivative is always going to be positive, which means that the function is always increasing, which means it is monotonic. If it is monotonic, that means it is invertible. So now we can find the inverse. So I'm going to let y equal x to the third, and then I'm going to switch x and y. So x equals y to the third. I'm going to take the cube root of both sides. So either y equals x to the 1/3, or you could write it as y equals the cube root of x. Since this is a function, I'm going to use better notation. I can say f inverse of x is equal to x to the power of 1/3, or the cube root of x. Since the inverse is also a function, because it is invertible, we can use this notation, which is just a little bit nicer. Okay, so that's it for this section. Let's sort of recap what we covered. We reminded ourselves what an inverse is, and that we can identify if two functions are inverses by composing them, plugging one into the other, and simplifying to see if we get x. We talked about how functions, when we're finding the inverse, we're really just switching x and y, and that inverse is a function, or is invertible, if the original function passes the vertical and the horizontal line test. This means that that original function is monotonic, or the behavior of that function never changes. We looked at a graph and we switched our x and y values of the graph so that we could graph the inverse. And lastly, we used the derivative to determine whether or not the derivative changes sign tells us whether or not our function is monotonic. And if it's monotonic, then the inverse is also a function. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.